Hey guys, this is softwaring upload demand. Today I come back by another Ansys tutorial on how can you do a reinforced beam analysis by using Ansys workbench. So as you know, ultra high performance reinforced beam is composed of a concrete, steel rebars, and even with steel stirrups. So as I showed you on the previous video that we can do such reinforced beam analysis by using Ansys Tutorial, but in this episode of Ansys Tutorial, I'm gonna show you the analysis in similar manner by using Ansys workbench. So as you see from here as a project tree, we try to create this reinforced part by using different tools on Ansys workbench, and also you can see that you have to select the material for concrete rebars and stirrups. Besides this, you have to select some cross-sectional area. By the way, this will be clear when we do everything step by step. You will see next. And also on the static structure part, we just apply the fixed support at one end and the displacement boundary condition at the other end. That means this beam is a simple supported beam which is fixed on the one side and roller support on the other. And also we apply the force at the center on some area, and as a solution stage we'll try to see the equivalent stress to roller formation equivalent elastic strain is the maximum principal stress using this software. So as you know the drill is part of video tutorial. I'm gonna show you how can you do this all using Ansys workbench step by step. Keep watching. I'm back after a break. To start with such analysis, we have to drag this static structural into this project schematic window. Once it is open, let us rename this reinforced beam. And then let us open this engineering data source to select the material for analysis. So as you know, the rebar and stirrups are made of structural steel. So this is the default material for Ansys workbench. This is the material property of this structural steel within elastic limit. So we have to add isentropic hardening. Let us add bilinear isentropic hardening here. So the yield strength and tangent modulus in megapascal will be as 600 yield strength and tangent modulus of 1000 megapascal. So from here you can see the bilinear isentropic hardening is added beside the modulus of elasticity of the material within elastic limit. And also from here engineering data sources, let us add a concrete from general materials here. Let us add here concrete. So the property of this concrete is given here, but we have to add multilinear isentropic hardening property or the different strain stress relationship within the plastic limit. So let us add this plasticity multilinear isentropic hardening. So the strain and stress gonna be let us take from here Excel. So as you see from here, the strain versus stress within plastic range of the concrete material. That means that there is entropic hardening of the material is here. So let us directly copy this one and input it here. And again the stress will be like this. So as you see, as you can observe from the stress strain plastic strain diagram here, six I mean 1 2 3 4 5 6 7 7 stress strain configuration or stress strain results are given here. So once we adjust the material property, let us proceed to the next step, which is geometry. So let us open this design modular part. Once the design modular is open, let us adjust millimeter as a unit and start our sketch here. So to start with, let us from concept, let us create a cross section, a rectangular cross section with 100 millimeter base and 100 millimeter width. So let us generate this one, and then let us extrude this cross sectional area into both symmetric, as the direction is both symmetric. Operations at material as the depth will be 500 millimeter on both sides. So let us generate this one. So this is the concrete part, and let us again create the rebar. So from create here point, so from detail here, type will be point, type will be construction point, definition will be using manual input. So let us put the construction point as this coordinate. Let us generate again. Let us add point to on the reverse direction from the previous one, minus 500. So let us generate this one. So as you can observe from here, one point is created here, and another is this point. So we have 2 points. So now we can create a line body from pointers. So from concept here, a line from pointers, and then let us select the two pointers by holding the control key. Let us apply. So let us generate. So the line body is created. The line body is created as you can see from here, and then let us from create body transformation mirror. So let us okay, let us before that, let me do something. So let us from concept, let us create cross section, circular cross section with 10 millimeter radius. So let us generate this one, and so let us adjust the cross section for this line body. So the cross section will be here circular. Let us generate. Then from here create body transformation mirror. So let us select this line body. I mean, not the mirror will be YZ, and the body will be this body. So let us generate this one. So the two-line body will be as this one and this one. Similarly, from create here body transformation mirror, let us say the mirror plane will be xz, and the body will be by holding control key this and this again. Let's apply. So let us generate this one. So we have 4 bodies with 10 millimeter radius. Cross-sectional area will be calculated by using this radius. So once we do that, the next will be creating the stirrup. So to do that, let us make normal to then from sketch let us create different circles out here, again here and here. So from constraint, all those circles have equal radius. Again this and this has equal radius, and then let us dimension horizontal from this line to this line will be again from this line to this line. So let us give 35 for all of those. And then from draw here, let us create line between two tangents between this circle and this circle, again between this circle and this circle, and again between this circle and this circle, this and this. So from modify, let us trim the inner one, this, again this. Let us generate this one, and from concept let us create another cross section with 5 millimeter radius. Let us generate this one, and then from concept lines from sketches here, the sketch will be this one. Let's apply generate. So from here 6 part 6 body, as is our sketch. So the cross section will be cross section 2, cross section will be circular 2. So let us generate this one, and then from here create a pattern. The geometry will be this one, and the direction will be, let us adjust manually. Let us do the reverse one. So the offset will be 100 millimeter, and number of copy will be 4. Let us generate this one. Again from here pattern, pattern type is linear, as the geometry will be this one again. So the direction as on the reverse direction, it is good. So let us generate. So those are the pictures. Once we do that, from here let us select face selector here, and let us make it normal to then let us create here an area for loading, for the load up, and then let us dimension as usual. So we already create what we have to do on the design modular. So let us extrude this one. Let us apply the operation is print face here. So the geometry will be this sketch. So let us generate. So we imprint that face. So let us hold face selector here. This is what we have to do on the design module. So let us close this one and proceed to the next step, which is model. So let us refresh this one. Once the mechanical answer workbench is open, the next will be doing everything step by step from here the project tree. So as you observed, as you can see from here, the first one is geometry. So here is our body, which is assignment is, or the material is a concrete, and there are other line bodies which are rebars and stirrups. So all those rebar and strips are made of structural steel, so we not need to change that. And the next will be a material. So we just use two materials, the concrete for the concrete beam and structural steels for rebar and stirrups. And the cross section, as you remember on the design model, we just use three cross section: rectangular for the beam, the concrete beam, circular one for rebars, and circular for stirrups. And also for the coordinate system, do not affect our analysis. So here on the meshing, we have to independently discretize the stirrups, rebars, and the concrete beam. So from here is the geometry. Let us suppress all, except before that let us suppress all bodies. Before that, let us start on the stirrups. Let us suppress all bodies. So the stirrups are here: 1 2 3 4 5 6 7. So let us unsuppress all of this. So as you can observe from here, here are the stirrups. So on the meshing stage, let us mesh by using 5mm element size. So let us generate this. So as you can see from here, here are the stirrups of this reinforced concrete beam. And also let us return back to geometry, and let us unsuppress all bodies, and then let us select the 4 rebars here, and then suppress all. And from the meshing stage, let us use 10mm element size, and then let us generate this one. So here are the 4 rebars which reinforce the concrete beam, and then let us unsuppress all, and then let us suppress all again. So here the concrete beam is discretized by using a 50 millimeter element size. So let us generate this one, generate this mesh. So I think it seems like good. So from the geometry part, let us unsuppress all bodies, and then let's proceed to the next step. We just discretized all the components here. So let us add this one. Let us show all bodies. So from here, let us again regenerate the mesh. Basically, the level of refinement depends on your interest. So the more you discretize, you will somewhat accurate result. So let us add this one, and this is the rebars and stirrups which reinforce this concrete beam. Basically, those rebars and stirrups are made of structural steel. Show all bodies, and so the next will be inserting the fixed support. Let us hold a selector. So let us select this edge, this edge, and then let us insert again the displacement support as this edge. So it is constrained in Y component and in Z component. In both Y and let us concentrate on both Y and X. Then let us apply the force this area. Let us hold face selector here as this area. So this force is defined by components. It will be minus 16 kilonewton force. So as the solution stage, we can put the equivalent stress again as a total deformation here, and then we can input the equivalent volume or elastic strain, and then we can see the maximum principal stress here. So once we do everything here, the final VP, we have to solve this one. By the way, it takes a longer time, so I already solved it before, so let me show you the result on that. So once the solution is completed, we will get the result like this. So as you can see from here, the equivalent stress will be distributed will be like this. So the maximum will be 60 megapascal, and the minimum will be 0.09 megapascal. So you can see as animated result due to that 16 kilonewton load. So this is the equivalent stress distribution, and you can see the total deformation distribution under this loading condition. So it is expectable that the deformation will be maximum at the point where the load is applied, and you can see even the elastic equivalent elastic strain. So it will be 0.006 maximum as this tip. And also you can see the maximum principal stress since it is non-ductile material, the concrete. So we have to see such results: the maximum tensile strain, the maximum principal stress. So it will be 19 megapascal at fixed support. So this is overall procedure on how can you do reinforced beamals by using Ansys workbench. I hope you guys enjoyed this video. Next time I will back with another more advanced video. See you later.